Have you, or a loved one, ever been the victim of a surprise physics lesson? If not, then brace yourselves as we introduce the photoelectric effect. What is that, and why should I care, we hear you asking? Well, dear viewer, come with us on a journey and let us enlighten you. What is the photoelectric effect? Having been first observed in 1887 by Heinrich Hertz, the photoelectric effect is the emission of electrons when a material is struck by light. It took until 1905 for Albert Einstein to publish his explanation of the effect, which after some thorough peer review led to him winning the 1921 Nobel Prize in Physics. Einstein's explanation begins with his hypothesis that light energy is carried in discrete quantized packets called photons. He theorized that the energy of a photon was equal to its frequency f, multiplied by Planck's constant h. In simple terms, this means that a photon with twice the frequency will have twice as much energy. It was found experimentally that this effect is different for each material. So, we set the constant phi to describe the minimum energy required to remove an electron from a material. This is known as the binding energy or work function. An incoming photon can give all of its energy to an electron. If this energy is larger than the material's work function, then the electron will lose that much energy breaking free and will be ejected with the rest as kinetic energy. As the work function is the least energy required to break free, this excess will be the maximum attainable kinetic energy for the electron. Another thing to note is that this equation is independent of the light's intensity. We know this as changing the intensity of the incoming light will only change the number of photons, and as our equation is per photon, we should see no change. We now have a solid prediction for how the photoelectric effect should behave, so how do we test it? One way is to use the setup depicted here, which consists of a vacuum photocell on the left connected to a digital voltmeter and a mercury vapor lamp on the right, which acts as our light source. To have a better idea of what this looks like, let's have a quick look at a simple simulation. This simulation depicts the inside of the vacuum photocell, where incoming photons hit our material acting as the cathode or negative side, and any ejected electrons strike the anode or positive side. As more electrons accumulate on the anode, its charge gets more negative until the voltage difference between it and the cathode is large enough to repel even the fastest electrons emitted from the cathode. This voltage difference is called the stopping voltage and is measured by the voltmeter. Electrons trying to pass through this potential will lose energy equal to the charge of the electron times the voltage difference. So our electrons will lose all kinetic energy when traveling through the stopping voltage. Rearranging tells us that our maximum kinetic energy is proportional to our stopping voltage. By plugging this into our original equation, we now have a relationship between frequency and stopping voltage that we can measure experimentally. Time to test this hypothesis. Let me introduce our two lab rats, science students, Tavish
Hello.
and Valentina.
Hello, help us. The narrator has
While these two
instructed
set up and
us
work through the
this way,
experiment,
please help us.
let us go over how they will gather their data and what we expect them to see. Recall our setup from earlier. The mercury vapor lamp is fitted with a diffraction grating that separates its light into 5 different wavelengths: yellow, green, blue, purple, and ultraviolet. While ultraviolet light is usually not visible to the human eye, the white section shown is made of a special fluorescent material that allows us to see it. The slit in the middle is what allows the light into the photocell to be measured. We have given our subjects 3 different filters. The yellow and green filters are used to improve results when measuring their respective colors as they are the most susceptible to interference from both the background light in the room and from potential overlap with the adjacent wavelengths. The last filter is used to vary the intensity of the light passing through. This will allow us to verify if stopping voltage is independent of intensity. So they will use this apparatus to measure the stopping voltage at each wavelength of light. They will then repeat this for each of the 5 intensities: 100%, 80%, 60%, 40%, and 20%. Our equation has the same form as the function y equals mx plus b, which for those not in the know corresponds to a straight line with a slope m and a y-intercept b. We can see that increasing m makes the line steeper and increasing b moves the plot up. We must remember to plot our values for the photon frequency instead of wavelength. This is easily done by using the relationship f equals the speed of light c divided by the wavelength lambda. By plotting this and then using a line of best fit, we can find a straight line that is as close as possible to all of our data points. Looking at our formula tells us that the slope of this fitted line will be Planck's constant h, and its y-intercept will be our material's work function, phi. We have also predicted that these two values should not change for our measurements at different intensities. Let's check back in with our victims, volunteers. They have finished collecting data and are probably free to go. Let's plot the 5 data points for 100% intensity. These look pretty linear, but let's check with a line of best fit. This fit gives us a Planck's constant value of 5.2 plus or minus 0.5 times 10 to the negative 34 joule seconds. Compared to the officially accepted value of 6.626 times 10 to the negative 34 joule seconds, we have the right order of magnitude, but the official value is not within our margin of error, so it's likely that our recruits have missed something. Let's plot all of our data and their fits to see what we can learn. This plot shows that what appeared to be random variation in the last plot was actually a consistent trend through all 5 sets of data. This suggests that our test gremlins didn't wait long enough for the voltmeter to stabilize, despite being clearly written in this terrible photo of a screenshot of the handout instructions. The voltmeter not stabilizing implies that these results are smaller than we expect, as if they have not stabilized, then they are still increasing towards the true stopping voltages. This is consistent with what we see, as our measured values are smaller than what is accepted. This also explains why the data for lower intensities gets smaller each time. We mentioned earlier that lower intensities mean less photons, which in turn means less electrons, so it will take longer to reach their respective stopping potentials. Knowing this, we can conclude that our values from the 100% intensity measurements are the most accurate. This gives us a final measured Planck's constant of 5.2 plus or minus 0.5 times 10 to the negative 34 joule seconds, which is around 22% smaller than the official value, and a work function of 1.01 plus or minus 0.21 electron volts, which is in the right ballpark for materials used in vacuum photocells, which are often at most a few electron volts. While the calculated Planck's constant is not accurate, it's not entirely off, which is a good sign. It means our method, if executed correctly, could yield much better results. While it's clear that the main source of inaccuracy was not letting the voltmeter stabilize, there were other things too. One of which was that the voltmeter needed external light to read, which contributed to background light. For some of the measurements, the output voltage bounced around quite a bit, even once it appeared to be settled down. So if we had a more accurate measurement tool, our results would have been better as well. You may have noticed we never told you why you should care. Well, this was a tactical ploy to keep you engaged. In the real world, The photoelectric effect is used to make photodiodes, which are in turn used to make several types of photoelectric sensors. These are used mostly industrially, but you can also find them in some types of smoke detectors, for example. You might have also heard of CT scans, which may use the photoelectric effect alongside X-rays in scanning. Older video camera tubes, camera analogs to CRT TVs, also use the photoelectric effect to capture images. Additionally, a related phenomenon called the photovoltaic effect, in which the electrons stay inside of a material rather than being ejected, is what gives us solar power. And just like that, we have finished our investigation of the photoelectric effect. We've had a good long look at what the photoelectric effect is and how it works, and showed that even when missing valuable data, we can still obtain a ballpark estimate for Planck's constant, despite our mystery material staying a mystery. That's all. Off you go now.